Assalamualaikum and hi. Our group represent the high performance liquid chromatography. So here is our members.
Now I will present to you our group member. First, we have Nur Aliana binti Roslan. Second is myself, Muhammad Iskandar bin Muhammad Hamroh. And the third one is Haide bin Haris. Now we are moving to introduction of Hplc or High Performance Liquid Chromatography. First, the definition of Hplc is an analytical technique used for separation of components, identification of components, and quantification of components in complex mixture. Hplc utilizes a liquid mobile phase, and the mobile phase is forced through a stationary phase under high pressure. The characteristic of Hplc is 1. Provided high resolution separation, and second, enable rapid analysis times. For our video presentation today, we have three objectives to complete. The first one is to determine the retention time of standard solution caffeine. The second one is to identify the caffeine peak in a sample T. And the third one is to determine the amount of caffeine in sample T using the response factor method. Now we are moving to theory behind Hplc. The principle of Hplc is based on the differential partitioning of analytes between the stationary phase and the mobile phase. The stationary phase, typically composed of a solid material packed into a column, interact with the analytes based on their chemical properties such as polarity and molecular size. The mobile phase, which is liquid under pressure, carries the sample through the column. The interaction between analytes and the stationary phase leads to varying retention times, allowing for separation. Key factors that influence this process include polarity, flow rate, and temperature. Polarity. Analytes with different polarities will have distinct interaction with the stationary phase, affecting their retention time. Flow rate. The speed of which the mobile phase is delivered can affect the separation efficiency and resolution of the analysis. Temperature. Variation in temperature can influence the viscosity of the mobile phase and behavior of the analyte within the column.
Methodology. Fill the mobile phase reservoir with the prepared Hplc solvent. In this case, we use water. Ensure the solvent is Hplc grade to avoid contamination. Degas the solvent using ultrasonication or helium spugging to remove air bubbles. Set the flow rate on the Hplc pump 1 ml per minute. Prime the pump to remove any air trapped in the system. Monitor the pressure to ensure system stability. Filter the sample solution using a 0.2 micrometer membrane filter to remove particulates. Transfer 10 microliter of the prepared sample into an Hplc vial. Place the vial in the auto-sampler or injector tray. Use the injector to introduce the sample into the mobile phase stream. Ensure the injection volume is consistent to maintain reproducibility. We use 10 microliter volume in this case. The mobile phase carries the sample through the Hplc column. Separation occurs due to differences in analyte polarity and column interaction. maintain column temperature as per the method. The temperature is setting at 40 degrees Celsius. The separated components pass through the UV detector. Set the detector wavelength at 275 nanometer for caffeine. The detector records signal intensities corresponding to analyte concentrations. Use data acquisition software to monitor the chromatogram in real time. Identify peaks based on retention times. Integrate peak areas for quantitative analysis using a calibration curve. Ensure proper waste containment to prevent spills. Dispose of the waste according to laboratory safety protocols. Function of each component. Hplc solvent or is called mobile phase reservoir to supply the mobile phase. The ratio of water and methanol 60-40 in Hplc grade used to carry the caffeine analytes through the system. Hplc pump to maintain a constant flow rate of 1 ml per minute, ensuring precise and consistent separation. Injector introduces 10 microliter of the prepared sample into the system. Hplc column to separate caffeine based on interaction with the reverse phase stationary phase. Detector measures the absorbance of caffeine for peak detection. Data acquisition unit to record chromatographic data. Example, peak areas, retention times for analysis. And the last of component is waste reservoir to collect mobile phase and analyze waste after analysis.
Next, I will present about the result and discussion. So this figure represents a calibration curve for caffeine, showing the relationship between the concentration of caffeine on the x-axis and the corresponding P area on the y-axis. The calibration curve is constructed using multiple known concentration of caffeine, which each point represents the area obtained from the chromatograph at the specific concentrations. The equations of the linear regression line is provided as y equals to 25080s minus 1745.2, and for the R square is 0.9928. Next, for the figure 2 is the chromatogram of caffeines. Illustrate the analysis of caffeine at a concentration of 2 ppm using a detector set at 205 nanometer. The x-axis represents the detection times in minute and the y-axis indicate the signal intensity in millivolts. A prominently and sharp peak is labeled caffeine, appearing at approximately 2.6 minutes. The well-defined shape and size of the peak confirm the successful detection and separations of caffeine under the given chromatographic condition. Next, the figure 3, which is chromatogram of caffeine in T sample, represent the detection wavelength for this analysis is 205 nanometer, which is perfectly chosen for its stable in detecting caffeine due to its UV absorbent properties, and is observed at approximately 2.6 minutes of retention time. This peak signifies the elutions and detections of caffeine for the T samples. Its sharp and well-defined nature suggests that the separation method was effective and the caffeine in the sample was successfully isolated from the other components. For the conclusions, we were able to determine the retention time for caffeine is 2.6 minutes. The different standard solutions taken for linearity show a linear range with correlation coefficients R square value of 0.9928. This method was recommended for routine analysis of caffeine in tea and coffee. That's all from our group. Thank you.